Alright, to show the hybridization of arsenic, first let's find the VSEPR structure to make things a little easier. Something I like to do is draw the Lewis structure as it gives me an idea how this molecule is shaped. I know that arsenic has 5 valence electrons. Iodine has 7, but we have to multiply that times 5. So that's going to be 35 plus 5, which means this is going to have 40 electrons. Let's see, that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40 electrons. I see we don't have any lone pairs. We have 5 atoms of iodine bonded to arsenic. So our total is going to be 5, which means this molecule is trigonal 5-pyramidal. Thanks to this, now I could draw my VSEPR structure. The repulsion between the arsenic and this molecule can be minimized by distributing the electrons towards the corners of the trigonal 5-pyramidal. Here, we're going to label this our equatorial. And that's 120 degrees. This is labeled our equatorial because these ones lie along the equator of the molecule. The other two are axial, which is 90 degrees. These are axial because they lie along the axis perpendicular to the equatorial plane. Let me show you some pictures so this could be a little more clear. As we can see here, this is our axial. We can even see here on the molecule that I made. We can make here our equatorial and equatorial. Now, let's begin our hybridization. But first, we need to draw our energy diagram so we'll be able to see this. Here we have an arsenic atom with just single bonds, and seeing those single bonds means that all of these bonds are going to be sigma. What are sigma bonds? The first bond made with any other atom is going to be a sigma bond, which are made from hybridized orbitals. One way to remember this is, remember, the first bond that you always see is going to be sigma. Now, let's draw our ground state, our energy diagram, so we'll be able to see the hybridization. This is the ground state. There we go. That's 4s. That's our 4p. That's our 4d. Arsenic has 5 valence electrons. This is going to be our excited state. Excuse me, drawing it lower. I kind of ran out of space. when we hybridize the normal atom of arsenic, we need to have 5 openings for hybridized orbitals. So the 4s, the 4p's, the 4p, and the 4d have to combine. So this is going to require the promotion or one of our s's from the 4s to our d orbitals. And it's going to look like this now. Once we do this, we can find out which type of hybridization we're dealing with. So this is our hybridization. So we have an S, 3 P's, and 1 D, which means our hybridization of this is sp3d. Now I'm going to show the bonded state. That's 1, 2, 3, 4, 5. Remember, this is sp3d. So that's 1, 2, 3, 4, 5. Now we have 5 openings to fill with our 5 iodines. That's iodine, and iodine is a P, which is 5P. Let me fix that. That's 1, 2, 3, 4, 5. So this one is the one that we're going to use to fill the spaces. There we go. There we go. This is our hybridized orbitals. And we could even see our sigma bonds here. That's 1, 2, 3, 4, 5. Now we can do our contour diagram. Let's see, I'm not the best drawer, so I'll do my best. Let's draw this a little better. There we go. This is going to be our sp3d hybridization. There we go. Let's draw the electrons. Now we have to draw our p's, our iodines, which are p's, and they're going to look something like this. There we go. Now let's label them. These are iodines. These are our sp3ds. sp3d. You can even see our sigma bonds here. That's 1, that's 2, that's 3, that's 4, and that's 5. Don't forget to label your iodine, which is a 5Ps. So this is our contour diagram Let me show you a photo so it looks a little more clear. As we can see from here we have our pi bonds. Our sigma bonds. Forget that, pi bonds are different. There's one in the back. These are our sigma bonds. We can still see our axial, which is 90 degrees. This is our equatorial. Which is 120 degrees. We can here see our pi, well, our p, our 5 p's. Alright, I hope this has helped you have a better understanding of hybridization, and thanks for watching.